Hello and welcome to Chapter 2. We're going to be talking about how ventilators work. So we'll get into a little bit more of the mechanics of how the machine actually functions to deliver breath. But the big thing here is when we're looking at people on life support, we need to understand just basically how the ventilator operates. And we'll cover different types of ones here. But the big thing is going to be focusing on the patient-ventilator interactions, or how the patient and the ventilator interacts with the breathing pattern, right? Because how we set the machine is telling the patient or delivering the tidal volume in a breathing pattern, a specific way. And so we're going to also look at how the patient's lung conditions can affect how the ventilator performs, right? As the patient's lung conditions change, which can be a breath-to-breath thing, that can affect how the ventilator performs and does its job of supporting that patient. So there are many different types of ventilators that are available for adults, pediatric, neonatal, in hospitals, home care, transport. You'll see a wide range of different kinds of ventilators. So being a master of the complexities of each of these devices is overwhelming, but they have a lot of things in common. And so we'll try to hit some of the things they have in common that allow them to be grouped in certain categories: pneumatically driven, electric, so on and so forth. So a big thing here is to study sort of how the ventilators function in general, so you have a good basic idea. And then the big thing is terminology can vary considerably between these ventilators, so we'll try to keep terminology pretty standard with this presentation. So the big thing is trying to look at some of the terminology differences. We'll try to do some of how the ventilator functions, of course, but we're not going to be able to review all available ventilators. There's just way too many out there for such a presentation. So big thing is making sure that you understand the literature provided by the manufacturer of the device that you're using, so that way you're a master of that ventilator. So be sure whatever you're using at your facilities that you have that manual, that you're able to understand how that machine works and how the patient and that machine can interface together, because once you understand that, you'll be able to troubleshoot and help care for that patient more effectively. So we just want a good basic better understanding of the operation of these devices, and that's the purpose of this lecture. All right, so basic early learning objectives. When we're looking at ventilators in the clinical setting, they were started to develop back in the 1950s, 1960s for post-op ventilators. They used to use the Emerson, right? If you want to look up a picture of that, they were usually used post-operatively in the 1950s and 60s. They're classified based upon their ability to deliver the breath. And now we have technological advances in the past, even during the past 50 years, that have dramatically changed the way these machines operate. And these changes required an update to how ventilators were classified. So when we're looking at classification of these ventilators, we're going to look at things that are how they're engineered, how the ventilator functions. Usually classification gives us a good foundation for looking at different aspects of ventilation as well. So a lot of people will rely on some of those earlier classification systems, but both classification systems will try to put together into a more commonly modern use for your patients. Big things here, we want to be able to define the user interface, describe what a ventilator's internal and pneumatic circuits are, what's the difference between those, the difference between a single lumen circuit and a double lumen circuit, and then identify components of the external circuit as well. The last part of this, our objectives here, is to explain the function of the exhalation valves, which will change depending on which machine you're using, compare the functions of the three types of volume displacement mechanisms, which we'll talk about those, and look at the function of the proportional solenoid valve, which is what we'll finish off with, and then I'll do some concept or clinical checks in there as well. All right, so internal function of the ventilator. So we have the user interface. A ventilator can be easily understood if it's pictured as a box that's just plugged into an electrical outlet or even a high pressure gas source, and the gas comes out the other side. The person who operates this ventilator sets certain dials or touch panels nowadays, which is great in some cases, on a control panel. So the control panel, or the screen that you're touching things, is known as the user interface, right? So whenever you're touching someone's breathing machine, right, that the changes that you're making on that screen is the control panel or the user interface. So we use that user interface to establish the pressure pattern of the gas flow delivered by the machine, so we can deliver it in different ways and different patterns to the patient depending on what's going on with their breathing characteristics. So we're using that user interface to establish the pattern of gas flow delivered by the machine. Inside the system, we're going to have a bunch of different settings that help regulate the desired output as well. So the touch panel is going to be the user interface. The control system is what's inside that interprets your settings and produces that output. So if I say I want a certain oxygen concentration of this, then the internal control system, so I'm doing that at the user interface, the internal control system is what then makes that change, right? It interprets my change that I did on the user interface, and then the control system inside makes that change for that patient. All right, so let's talk about the power source, right? The major components of the ventilator, and you're going to have a wide variety out there, but a ventilator's major power source is what gives it the energy that enables it to perform the work of ventilating the patient. So we talked about in chapter 1, you can either have positive pressure ventilation or negative pressure ventilation, like the iron lung, those things that we were looking at there. The power used by the ventilator to generate this positive or negative pressure is provided by either an electrical component where it's plugged in or on a battery of some sort, or a pneumatic compressed gas source, right? And so you'll see those different types of ventilators out there. So electrically powered ventilators, and we'll start with those here. The electrically powered ventilators here rely on electricity from a standard outlet. So that's 110 to 150 volts. And when we're looking at this, we can use a lot higher voltage in the United States, right? We could use 220 in other 60 hertz in the United States, but we can use higher voltages in other countries as well. So that's something else to be careful of if you're going to do international trips or anything like that. A lot of times they'll have a rechargeable battery that's internal. A DC battery may be used, but battery power is typically used for short periods of time for transporting a vented patient or in a home care patient as a backup power as well. So those are all things that we can look up there. Especially if their electricity fails at their house, they should be able to have a backup battery source to help run that ventilator so they can keep going. There should be an on and off switch that controls the main power sources. The electricity provides the energy to operate motors, electromagnets, which will tell the ventilator what to do, potentiometers, rheostats, microprocessors, which in turn control the timing of the breath, the timing of the mechanisms for inspiration or for allowing for expiration to occur, or even gas flow, or even the alarms, right? The alarms themselves need power. So electrical power can also be used to operate other devices inside the ventilator besides those, like fans, bellows, solenoids, transducers. All those devices help ensure a controlled pressure and a gas flow to the patient. So these are very important internals, and so that electrical energy is going to be pretty important to have for those ventilators that have all those things. Most current generation intensive care unit ventilators are typically pneumatically powered devices, right? They're typically pneumatically powered devices. right? I just repeated that on purpose, right? So the machine uses a one-way, one or two 50 psi gas source built into an internal reducing valve that the operating pressure is lower than the source pressure. So we'll plug the ventilator, oxygen, and air into the wall, and those are those 50 psi sources, and they will have an internal reducing valve that will help operate the machine at that lower pressure. So pneumatically powered ventilators are classified according to the mechanism that they use to control the flow of gas. So there's two types available. There are pneumatic ventilators with fluidic ventilators and pneumatic ventilators that use needle valves like Venturian trainers or flexible diaphragms or spring-loaded valves to control flow, volume delivery, and inspiratory and expiratory functions. So there's a lot of different kinds in here. The picture here that you see on the screen, this is a Bird Mark 7, right? And it was originally used for prolonged mechanical ventilation. And you'll see this still in some facilities. Some facilities still use them, and you'll see them probably in our lab. We have one. These are ventilators. They're an example of just a pure pneumatic ventilator. There is no electrical component associated with it. You can plug it into a 50 psi source, even a transport oxygen tank, and you can run it just off of that, right? So they've been used to administer what was called IPPB treatments, or intermittent positive pressure breathing treatments, and they helped with volume expansion and delivering medication to those patients. So when we've seen those, they were widely used for not only breathing treatments, but even for mechanical ventilation. So they were great to aerosolize medications to people that were spontaneously breathing that had reduced ventilatory function, like patients that had spinal cord injury or neuromuscular issues or chronic obstructive pulmonary disease patients that didn't have a strong inspiratory flow rate. Well, this ventilator or this machine delivers that medication with a positive pressure to help with distribution of that medication into their lungs, especially if they have a hard time getting that breath into their lungs, like a neuromuscular spinal cord injury, anything like that, anything that causes muscle weakness. Fluidic ventilators usually rely on the principles to control gas flow, like the wall attachment beam deflection, which we'll talk about here. The Coanda effect is the big thing that we talk about there. So an example of a ventilator that used fluidic controls, there was one called the MVP10, M as in Mike, VP10, and there were a ventilator that just used pure fluidics, right? They are only occasionally used to provide ventilation to patients in an acute care setting, so they weren't for long term. But when we're looking at those are very, short. Very few of those are used today, right? But most pneumatically powered ICU ventilators also have an electrical power source that's incorporated to energize the computer that controls the ventilator function. So now they're still pneumatically controlled, right? You go to a modern day ICU, you're going to see a pneumatically controlled ventilator, but that's going to have an electrical power source incorporated to give energy to the computer and the functions of it as well. So the gas sources and mixtures of air and oxygen supply the power for ventilator to function, and they allow for various FiO2 concentrations, but the electrical power is required to operate the computer microprocessors, the controls, the capacitors, the solenoids, the electrical switches, the phrasing of the ventilator, regulating the inspiration and allowing the patient to exhale. And it even monitors the gas flow and controls the gas flow. So the ventilators are pre-programmed with modes traditionally that are stored in the microprocessors. And they can be updated pretty rapidly by installing new software programs. So you're going to have a random access memory, or RAM, which also is incorporated into the ventilator central processing unit. that can be used for storage of data. So we can go back and you can see ventilators, a lot of them, the newer ones, will have trending on them. So we can see how's the patient done in the past 4 hours, 24 hours, so on and so forth. So we could actually trend data, and it will actually store data for some of those patients for us to help us better see which direction this patient is going. So it will allow us to also see other things like, hey, flow measurements and airway resistance and compliance. Has their compliance been improving? Is their compliance been trending down? Right? So these are very important things that these microprocessors allow us to do, so that way we can take better care of our patients. So when we're looking at positive or negative pressure generators, when we're looking at this, the gas flow into the machine or into the patient, right? The gas flow into the lungs can be accomplished by using 2 different methods of changing the trans-respiratory pressure gradient. The pressure at the airway opening minus the pressure at the body surface. So pressure at airway opening minus pressure at the body surface is the trans-respiratory pressure gradient. So a ventilator can change the trans-respiratory pressure gradient by altering either the applied pressure to the airway opening or the pressure around the body's surface. So the pressure at the airway opening, we're looking at usually positive pressure ventilators. The body pressure surface is usually used with negative pressure ventilators. So with positive pressure ventilators, gas flows into the lungs because the ventilator establishes a pressure gradient by generating a positive pressure at the airway opening, in contrast to the negative pressure, like I said before, where it goes around their chest wall, their abdomen, or their whole lower half of their body, like you see with those iron lung patients, to generate that negative body surface pressure that then pulls on the pleural space and the alveoli to expand for a breath in. Right? So positive or negative pressure generators is what we're looking at there. The control systems and circuits, right? So that's the next part we're talking about here. The control system or the control circuit. This is the decision-making system that regulates the ventilator function internally. So we can use mechanical or electrical devices, electronics, pneumatics, fluidics, or even a combination of those to sort of help with decision making of the ventilator. So when we're looking at these, we can see that there's an advantage to adding a microprocessor, right? So microprocessor technology has allowed us to get new generations of ventilators that give feedback loop systems, right? So most ventilators that are not microprocessors, do not use microprocessors, are called open loop system. Open loop systems, which means you set the control like a tidal volume, and the ventilator delivers that volume to the patient's circuit. Well, this is called an open loop system because the ventilator can't be programmed to respond to changing conditions. If gas leaks out of the patient's circuit and doesn't reach the patient, the ventilator can't adjust its function to correct for that leak, right? So it's open loop. It simply delivers that set volume. It does not measure it or change it as a response to what's going on with that patient. Right? So it's just sort of set it and it's not going to change it, right? Closed loop systems, however, are often described as your intelligent systems because they compare a set control variable with the measured control variable. And you'll see that a lot on the ICU ventilators. You have your settings and then you'll have what the patient's doing with those settings. So a closed loop system is your intelligent one. They compare your set variable with what the patient is doing, the measured variable, which in turn allows the ventilator to respond and change to the patient's condition. So some closed loop systems are programmed to compare tidal volume with your tidal volume set to your measured tidal volume exhaled by the patient. If they differ, the control system inside the ventilator itself, without you doing anything, the control system can alter the volume delivery inside by itself. So that way it makes sure it's correcting for any leaks. It makes sure it's correcting for anything that could be going on between the set and measured level. So one of those, back in the day, there was a mode called mandatory minute ventilation. All right, and that was a closed loop system. So what happened is you, the operator, selected a minimum minute ventilation. Say I want this patient to have a minute ventilation of 10 liters per minute, right? So you set that on there. So the minute ventilation, the setting is at the lower than the patient's spontaneous minute ventilation. So the ventilator monitors the patient's spontaneous minute ventilation, and if it falls below that set value of 10 liters a minute, the ventilator will increase its output, so it will support them to help get them up to that minimum minute ventilation. So the ventilator was a closed loop. It would see, okay, this person's not getting the minute ventilation they need. I'm going to increase that. I'm going to augment that. So that's that open loop versus a closed loop. And so that would be that closed loop system. So let's say a ventilator is programmed to monitor your non-invasive saturation, your SpO2. Right? So if your saturation drops below 90 for longer than 30 seconds, then the ventilator in a closed loop system can be programmed to activate an audible alarm that can't be silenced, and then a red flashing visuals. It's going to throw a whole light show at you. The ventilator could also be programmed to increase the oxygen percentage to 100% until the alarms have been answered or deactivated by the user, right? That'd be us. So that would be an example of a closed loop system, or an open loop. Is that an example of a closed loop or an open loop system, right? So there are advantages to this where it could potentially help with safety, but what happens if the pulse oximetry just became unstuck from the patient's finger and we're giving 100% oxygen and causing alarm fatigue and causing a lot of noise and causing a lot of stress on everybody when the pulse ox just came off their finger, right? So there are some advantages and disadvantages of this type of system. When we're looking at fluidics, and that's why I have the picture here, down here, basic components of a fluidic or pneumatic mechanisms. When we see up here, this is an example A of a flip-flop valve or beam deflection when you're looking at this picture here. When continuous a pressure source that's in inlet A enters the wall, attachment occurs to the output is established, and the signal gas pulse from C1 deflects the beam to the outlet O1, right? So when we look at this, the wall attachment phenomenon is called the Coanda effect. And this is what people use actually when they're flying an airplane. So you see the flat part on the bottom of the wing is the flat part, and then you have the curved part at the top of the wing, where you're going to have high pressure that's created at the top of the wing because it's rounded part, but right behind that curved part, you're going to have a low pressure. So therefore, ultimately, you're going to have higher pressure under the wing than you do above the wing, and that generates a Coanda effect where you're going to have lift. You're going to have the air movement, right? So it deflects that air movement and allows for that jet to be changed, that air jet to be changed, and so then we can cycle a ventilator. Pretty straightforward, right? So when we're looking at that jet flow causes a loop of lateral inflection, and it will go, and the wall is then adjacent to the low pressure, that vortex bubble, just like in an airplane wing, and it bends the jet toward the wall, the figure on the right here. So we're seeing that change from here to here. So we can change how a jet moves inside with some of these fluidic ventilators. So you might see a ventilator out there, and we had some of these that we'd use for MRI. We've had some of these that are used for transport ventilators that have no electrical components, especially for MRI, that can be set and altered by the MRI machine. Now there's modern day MRI ventilators that don't have to use this system quite much anymore, but I think it's a good way to sort of see how fluidics and how just air vortexes can change the breath delivery. So when we're looking at a power source, a ventilator's power source enables it to perform mechanical and pneumatic operations. So when we're looking at this, the internal hardware that accomplishes the conversion of electrical or pneumatical energy into mechanical energy. So it gets the electrical output energy and it needs to change it to mechanical energy to deliver a breath to a patient. And so what that is called when that happens is the power transmission and conversion system. So it consists of a drive mechanism and an output control mechanism. So a drive mechanism is the mechanical device that produces the actual gas flow to the patient. So an example of a drive mechanism, you're like, Derek, I don't know what you're saying, right? I hear the words, I don't know what you're saying. So an example of a drive mechanism is a piston that's powered by an electrical motor. So you plug in the electrical motor and then it tells this piston, okay, move back and forth, move back and forth, move back and forth, right? So that is an example of a drive mechanism, right? It's a piston powered by an electrical motor. So the output control consists of one or more valves that regulate the flow to the patient. So if you look at this from an engineering perspective, and I know you're like, I don't want all this information, but from an engineering perspective, the power transmission and conversion systems can be categorized as volume controllers or flow controllers, right? So when we're looking at volume controllers or flow controllers, that's pretty much what the ventilator is controlling inside to deliver that breath to the patient. So an appreciation of how volume and flow controllers operate requires an understanding of compressors, also known as blowers, right? So compressors reduce internal volumes, right? A compressor compresses, it reduces, right? It makes something smaller. So a compressor reduces internal volumes within the ventilator to generate positive pressure required to deliver the gas to the patient, right? So it's going to compress the gas, make it smaller, so it can deliver the breath to the patient. It creates that positive pressure. So these compressors can be driven by a piston, like what we talked about before, or they can have rotating vanes or moving diaphragms or even bellows for those classic old school pictures, right? You'll see those old ventilators that have the bellows, right? So hospitals, when they use large piston, they actually used a large piston type water cooled compressors to supply wall gas to the outlet. So how do you get the pressure when you plug your ventilator into a wall, or when you plug your oxygen Thorpe tube into a wall? Well, the hospital uses a large piston water-cooled compressors to supply pressure to the gas outlets. So many ventilators use these as a power source. They use that pressure from the wall outlet as a power source. So a lot of ventilators out there have an internal built-in compressor that can be used to power a ventilator if the wall gas somehow fails, right? We lose pressure to that area of the hospital, then they have an internal compressor that can kick in and help that patient still get that breath, right? It's still using an internal compressor of the machine. So that is a nice feature to have, especially if for some reason gas fails to that area. There are volume displacement devices that we'll talk about here. They include bellows, pistons, bags, bag into chamber systems. But when we're looking at this, current ICU ventilators use a flow control. So they're going to look at a lot of flow control valves to regulate gas flowing to the patient. So these flow control valves operate by opening and closing either completely or in small increments to deliver that breath. So these valves, they're driven by different motor-based mechanisms, so they have a very rapid response time and a lot of flexibility in flow control. So they operate as a way to help with that breath delivery from millisecond to millisecond in some of the modern ventilators. So these flow control valves include proportional solenoid valves and digital valves with on-off configuration. So we can change different things within breath to breath or even in the middle of a breath sometimes. So a proportional solenoid valve is designed with various configurations to modify the gas flow. So how do we modify the gas flow? Well, that's a solenoid valve that's doing it. So a typical valve incorporates a gate or some sort of plunger, a valve seat, and electromagnets. This is why these machines got to be MRI compatible at least. A diaphragm, a spring, electrical contacts. So what happens here, an electrical current flows through the electrical magnet and creates a magnetic field. Okay, we got a magnetic field that pulls a plunger and opens the valve. So electrical current goes through a magnet that creates a magnetic field, which then pulls a plunger and opens a valve. The amount of current flowing through the magnet influences the strength of the magnetic field. And the strength of the field determines the position of the plunger, right? So the design of the plunger can vary from ventilator to ventilator. So the more we put into it, the more that valve can change, right? So solenoids can be controlled in 3 ways: by electrical timers or microprocessors, by manual operation, and by pressure. Alright, so those are your 3 things that can control solenoids: electrical timers, microprocessors, or by pressure, right? Electrical timers and microprocessors have electrical currents that passes through the magnets that opens the valves, right? What we just talked about. Manual operation closes a switch, sending a current to the magnet and the opening valve, so we can manipulate that ourselves. Pressure changes generated by a patient's inspiratory effort can cause the diaphragm to move, which then closes the electrical contact and opening or closing the valve. So ventilators that have that, your most modern day ventilators from the Puritan Bennett 840, the Galileo, which we have those in our lab, but now even the newer modern ones also have that ability. So even a lot of these will have a digital on-off configuration, so the valves can operate together. So each valve is either opened or closed, and you'll see every once in a while what's called a safety valve is open, right? Well, that means someone was trying to breathe when the ventilator wasn't delivering a breath or wasn't set to delivering a breath. Well, that's there as a safety mechanism to allow the patient to breathe, even if for some reason a microprocessor or something like that fails. So it'll still allow flow to the patient so they can breathe even if something's malfunctioning, which is a good safety feature. You want that. So when we're looking at a particular valve, usually produces a certain flow by controlling and opening and closing the size of the orifice, right? So if we want a bigger flow, bigger orifice, smaller flow, smaller orifice, right? So the amount of flow varies depending on which valves are open as well. Like the little infant start ventilator uses this type of thing, so we can have very, very small flows for very small volumes and so forth. So when we're looking at the different circuits, if a ventilator's internal circuit allows gas to flow directly from its power source to the patient, it's called a single circuit ventilator. So the gas, the source of the gas may be either externally compressed from the outlet there, or an internal pressurizing source such as a compressor from the ventilator itself. So most ICU ventilators that are manufactured today are classified as a single circuit ventilator. So they have that compressor. They have some sort of something that compresses the gas internalized, so that way it can deliver the right amount of pressure to the patient. There is another kind out there, an internal pneumatic circuit ventilator that is called a double circuit ventilator. And these machines, the primary source generates the gas flow that compresses the mechanism, such as bellows or bag. The gas in the bellows or bag then flows to the patient. So that is something that's out there. But when we're looking at this, a double circuit ventilators are not very widely used in the market currently as of this recording. But most commercially available intensive care unit ventilators are single circuit, microprocessor controlled, positive pressure ventilators with a closed loop element of logic in the control system. That was a big mouthful, but let me talk about that again. All right, when we're looking at this, most ventilators, most modern ICU ventilators, so that's a big thing there. Most commercially available intensive care ventilators are single circuit. So they have an internal compressor. They have microprocessor controls, so we can control different variables of how the breath is delivered, including oxygen concentration, volume, flow, so on and so forth. And they're positive pressure, so they deliver positive, higher mouth pressure compared to the alveolar pressure. And they have closed loop elements of logic. In other words, they see a leak in the system, they're going to alarm and say, hey, there's a leak in the system, or hey, there's excessive pressure in the system, right? So they have closed loop elements of logic in their control system. So once again, most commercially available intensive care ventilators are single circuit, microprocessor controlled, positive pressure ventilators with closed loop elements in logic in their control systems. So it doesn't mean that they'll adjust absolutely everything directly with the patient, but they may just go ahead and alarm, or they may terminate a breath if there's too much pressure, right? Things like that can easily happen on this. So the external pneumatic circuit of a patient, or a patient circuit, connects to the ventilator and to the patient's artificial airway, whether it's an endotracheal tube or a tracheostomy tube. The circuit should have several basic elements to provide a breath, right? So during inspiration, the expiratory valve closes because, right, you don't want the breath being delivered to the patient. You don't want it just going through the other side of the circuit. So during inspiration, the expiratory valve of the ventilator closes, so gas only goes to the patient lungs. It makes sense. In early generation ventilators, the exhalation valve was actually mounted on the exhalation line of the patient's circuit, right? Isn't that crazy? But with that arrangement, the expiratory valve change line, which powers the expiratory valve, also must be present. So there was a lot of stuff that had to be there and could be exposed to a lot of damage. But when the ventilator begins inspiratory gas flow through the inspiratory tube, the gas also flows through the charge line, closing the valves, right? So we know that gas is being delivered only to the patient. It's not going to the expiratory, not going just through the ventilator machine and through the inspiratory limb into the expiratory limb. It's going to the patient. During exhalation, the flow of the ventilator stops, and the charge line depressurizes, so it stops pressurizing the charge line, and the exhalation valve then opens and allows the patient to exhale. So they're able to exhale passively through the expiratory part. So that way the patient can completely exhale, hopefully. In most current ICU ventilators, the exhalation valve is on the inside of the ventilator and is not visible, but a mechanical device like a solenoid valve typically is used to control these internally mounted exhalation valves. So when we're looking at most of these, a lot of them will be internal. So when we're looking at this, the power transmission conversion system, we already talked about this one a little bit, but as a quick review, right, this enables the ventilator to perform a mechanical or pneumatic operation. So our example before, this is what is the output control mechanism. So it's the device that produces gas flow to the patient. An example was, the example that we did earlier was a piston that's powered by an electrical motor. You plug it in and then this piston just moves back and forth, right? So that's an example of this. So the output control consists of one or more valves that regulate gas flow to the patient. So this is where we talked about it. This allows it to convert that electrical energy to mechanical energy to then deliver that flow to the patient, right? So you're going to have a drive mechanism that produces gas flow to the patient and an output control that regulates it, and that's the opening and closing of those valves. Yay, compressors. So compressors are an application of how volume and flow controllers operate. And when we're looking at this, this is an understanding of compressors. Compressors are also known as blowers, so you'll see that in your reading material. But usually we talk about them as compressors. So what do compressors do? Well, they reduce internal volumes. They create compression within the ventilator to generate positive pressure. We've already talked about this. And that will then deliver that gas to the patient. So they can be driven by a piston, right? They can use rotating blades. They can use rotating or moving diaphragms or bellows. Hospitals use large pistons to help pressurize the gas system as well when we were talking about these. So there's a lot of different types of compressors that can be built in there, but it helps the gas to still be delivered to the patient. In the event of an outlet, a gas failing, then we can still deliver that gas to the patient. So compressors are very valuable in our treatments. So when we're looking at these different types of compressors, first one is the volume displacement devices. So when we're looking at these, the bellows were the classic one that you've seen in all those old movies, on those old ventilators that had these bellows that would move up and down, right? So we had spring-loaded bellows, which this is that picture here of a spring-loaded bellow. Let's see, here we go. Spring-loaded bellow. All right, so it had an adjustable spring on top of the bellow, right? And you'll see that spring right here, right? You see that spring on top of the bellow that applies force per unit of area or pressure, right? So force over an area that would tighten the spring and creates a greater force, therefore greater pressure. So that bellow would then contain pre-blended gas, your air and oxygen concentration, and that would be administered to the patient. So the old Servo 900C is an example that used spring-loaded bellows to deliver that. Those devices usually aren't manufactured anymore, but it's pretty important to sort of see how the modern ventilators have developed, right? So this isn't something I would expect you to be able to troubleshoot modern day, but it's kind of interesting to see how these have developed and where we've come with our technology. In a linear device, when we're looking at these linear devices, these use an electrical motor that are connected by a special gearing mechanism or a piston, a rod, or arm, and that's what you're seeing in these other devices up here. And you'll see those pictures in your reading material as well. So they're connected by a gear mechanism in a rod or arm, and the rod moves the piston forward inside the cylinder, housing a linear fashion at a constant rate, so it's very controlled. And then you have some high frequency ventilators that use linear direct to drive pistons. So incorporating a rolling seal or using low resistance materials has helped eliminate the friction that occurred with a lot of these devices. They would overheat. So they developed even better materials from those. Back when I first started, there was the Puritan Bennett 760 that had a linear drive piston to use its breath delivery. So this type of drive mechanism is called a rotary drive, and that's what you see at the top here, the rotary drive. The rotary drive mechanism is called it's a nonlinear device, and it uses that to drive the system. An electric motor, when we use these, the electric motor is connected by a special gearing mechanism to the rod or to the arm. The rod moves the piston forward inside the cylinder, and it moves that piston at a constant rate. So that's where we had a lot of that stuff really worked pretty well on those patients. So the resulting flow pattern was slow at the beginning of inspiration and achieves the highest speed at mid-inspiration and tapers off at the end. So this flow pattern that was delivered to the patient with these machines is called a sine or sinusoidal waveform. So that was used for some of the home care ventilators back in the day, but a lot of patients, when we're spontaneously breathing, will breathe in a sinusoidal waveform. However, in a sinusoidal waveform is just that classic sine waveform, just like what you remember from your math. Yay, memories. So when we're looking at this, most patients, if they're really struggling to take a breath in, if they're very air hungry, they want to take in a breath really fast at the beginning. So that's why we'll see some of these ventilators where it'll allow them to take a breath really fast and then sort of taper off its flow delivery as well. So you'll see that we'll change some of these mechanisms for different types of ventilators. Current ICU ventilators use flow control valves. So flow control valves, they regulate gas flow to the patient. So we get, instead of just a sine waveform all the time, now we can regulate the gas flow and change it to different patterns. So we can customize the interface with the patient a lot better. So these flow control valves operate by opening and closing either completely or in small increments, right? They're driven by different motor-based mechanisms inside the machine, and they have a very rapid response time and great flexibility in flow control. So even within a breath, it can change the flow that the patient's pulling. If they want to pull more or less, it can do that within a breath, milliseconds, right? So flow control valves have come a long way. They include the proportional solenoid valves and digital valves with an on-off configurations where it can close them and open them pretty quick. A proportional solenoid valve, we talked about this before, can be designed with various configurations to modify gas flow. So it could use a plunger, a seat, electromagnets, a diaphragm. We've already talked about this. But what happens is an electrical current flows through the electromagnet and creates a magnetic field. That magnetic field pulls a plunger valve open, right? And the amount of flow going through there influences the strength of the magnetic field, which then determines the position of the plunger or how much gas can flow through there. So it can bigger, smaller breaths, so on and so forth, right? So solenoids can be controlled in three ways: by electrical timers or microprocessors, by manual operation, we already talked about that. With microprocessors, that electrical current is what will open the valves. Through that magnet was what opens the valves. Manual operation usually closes a switch, sending it to the magnet that would then open the valves. So pressure changes when the patient's getting their inspiratory effort can cause the diaphragm to move and therefore open these valves. So it's kind of a good safety feature like we talked about before when we're looking at these. So that digital on-off valves are other types of pneumatic control valves. Each one of these controlling a critical orifice that's specified by flow. So there's a number of discrete steps when you're looking at this picture. There's a number of really discrete critical steps that allow the patient to get their gas delivered. So this machine is way more than something that just delivers just a set breath at one set rate, and so on and so forth. There's so much more complexity. So that tells you there's a lot of stuff that goes into this machine delivery of the breath, which means that there's a potential for not only mechanical and electrical failure and pneumatic failure that can all impact gas delivery and flow rate to the patient. All right, so we just went through a lot. So what are some concept checks that we have here? The major components of a mechanical ventilator include high pressure gas source, a control panel or user interface to establish a pressure pattern or gas flow. So high pressure gas source and a control panel or user interface is a lot of people say. So that's your touch screen or hard buttons, depending on which machine you have, right? So but include either a high pressure gas source and a control panel of some sort to put in our variables to establish the pressure and gas flow, right? Ventilator power sources operate on an electrical or pneumatic power. These power sources operate on electrical or pneumatic power. Electrically powered ventilators may rely on an AC wall outlet or a DC source. It's like a battery, especially for those patients, spinal cord injury patients that are ventilator dependent. Might have obviously a battery backup when they're in their wheelchairs going around, right? But pneumatically powered ventilators are classified as pneumatic ventilators or fluidic ventilators. Pneumatic powered microprocessor controlled ventilators use compressed gas, right? That's what we plug into the wall. They use compressed gas input to power or drive inspiration, and then they use electrical power to control the characteristics of the breath. So they use the compressed gas to deliver the breath, but they need the electrical power as well. With positive pressure ventilators, gas flows into the lung because the ventilator establishes a pressure gradient by generating positive pressure at the airway opening, right? We generated a positive pressure at the airway opening. So when we're looking at this with these concepts, I hope that you're sort of getting the big picture with it and try not to get lost in the little things. So here are just some brief things that we touched on here. When we're looking at this, the control panel, this is also known as the user interface. The control panel or user interface has various touchpads or touch screens for setting components such as your tidal volume, the rate, your inspiratory time, alarms, even your FiO2. So the control panel controls a lot of stuff. This is the interface. This is what you set your settings on. When you have an open loop system, so open loop systems, this is the second point there, open loop systems, the ventilator cannot be programmed to respond to changing conditions. You set a tidal volume of this much, and even if it's too little has been delivered, if there's a leak in the system, it's not going to change anything. It's not going to know that, and it's not going to do anything with that. So with open loop systems, the ventilator cannot be programmed to respond to changing conditions. In contrast to this, closed loop systems often are described as your intelligent systems because the ventilator can be programmed to compare the settings that you have in there to what the patient's doing, so the patient's response to those settings. So therefore, we can have that adjustment or alarms that can happen depending on which mode we have the patient in. The major components of the patient circuit include a main inspiratory line, which connects the ventilator output to the patient's airway adapter or connector. So think about an inspiratory limb of a ventilator, right? Connects the ventilator output to the patient's airway adapter, right? An adapter that connects the inspiratory line to the patient's airway, so that's the Y of the circuit. An adapter that connects the inspiratory line to the airway, right? And then an expiratory line, once they exhale, an expiratory line that takes the gas from the patient to the exhalation valve. And then finally, your last one is an expiratory valve that allows for the release of gas from the expiratory line into the room air. So that's something that we'll look at there. And most of these ventilators out there will have some sort of HEPA filtering system, so when the patient exhales, that they have some sort of airborne disease going on, that could actually help protect the providers in the room.